I'm Jason Samuel Pangestu, final year of Mechatronic Engineering. Today, I'm going to present about my final year project. So this project focuses on developing a low-cost articulated autonomous robotic arm with vision recognition. The main task of this robotic arm is to pick and place the target objects autonomously on the semicircle stage. In this project, the sensing system for the vision recognition is performed in real time by using base servo and sensors. This will obtain the Cartesian coordinate of the target object and send to the Simulink software. Then, the robotic arm can perform the pick and place simulation. The agenda for this presentation is first to explain briefly about the background, then I will explain for each of the objectives for this project. The first one is the robotic arm design. This section will explain the robotic arm model as well as the kinematic model. The second one is the overall hardware. In this section, I will show the sensing system in here. The third one is the object's color detection and tracking. The fourth one is the pick and place robotic arm simulation. In here, I will focus on the trajectory planning of the robotic arm. Next will be the overall system flow and demo. And the last one will be the future improvement for this project. Now, start from the background. Robotic arm is widely used in different industrial applications, and the most common one is the pick and place in manufacturing sector. In this sector, an articulated type with revolute joints are commonly used. This type of robotic arm is usually equipped with camera as the sensors. The placement of the camera can be at the end effector, like in here. This is the eye in hand configuration, or it can be fixed to the ceiling. This is the eye to hand configuration. And in this project, a different design is proposed where it has eye in hand configuration, but the camera is put on the base. The type of the structure is the simple articulated where it has 3 revolute joints. Now it's the robotic arm design. The robotic arm structure and the overall model are designed using 3D model Solidworks software. The first one is the support, and it is fixed to the ground. This one is the support. The second one is the base, which acts as link 1 for the robotic arm. This base can rotate 180 degrees to scan the target object. Next is the upper arm, which acts as link 2 for the robotic arm. This link can rotate forward and backward for a limited angle. The third link is the forearm. This link can also rotate forward and backward for a limited angle. And the gripper palm and the gripper are also attached to this part. And as we can see in here, the end effector is in here, is the contact point between the gripper jaw tip and the target object. Meanwhile, this is the semicircle stage with the target objects at the above. For the actuators, I use 4 hobby servos. The first one is the MG996R servo. The function of this servo is to rotate the base part, and the rest of the MG90S servo will rotate the upper arm, the forearm, and also the gripper jaw. This slide shows the kinematic model of the robotic arm. It can be seen from the left picture that the coordinate system is composed of x, y, z axis. So the x is right one, y is green, z is blue. In terms of robotic kinematic, there are 4 important parameters. The first one is theta or joint angle, as we can see in here. D is link offset, this one. A is link length, these two. Alpha is link twist, like in this DH notation. So these 4 parameters will be implemented by DH notation. So this DH notation basically deal with the transformation of the coordinate from one joint to another joint. And in this rule, the direction of counterclockwise is positive. Next is the inverse kinematic analysis. From the given kinematic model, we can do the analysis for the inverse kinematic. Basically, the function of inverse kinematic is to calculate the required joint angles. So the end effector position goes to the target coordinate. The analysis starts by assigning a specific coordinate for the end effector. In this case, this is the end effector that has coordinate of xc, yc, and zc. And we need to find each of the joint angles, joint 1, 2, 3. This is the more detailed view of the inverse kinematic analysis. From this one, the top view is the top view of the robotic arm. From here, we can get joint angle 1. From the side view, we can get joint angle 2. And from another side view, we can get joint angle 3. And these are the corresponding equations for the inverse kinematic. Next, I will explain about the overall hardware that I use for this project. So according to the picture, the overall hardware is consisted of several parts. The first one is the Arduino Uno. This microcontroller is used to control the base servo for the object tracking. It is also used to obtain the data from the ultrasonic sensor. Then, the power supply is used to power up the base servo. Then small values of capacitor is used, as it is shown in number 3. For the sensing system at the top part, it will be explained more detail in the next part. While number 5 is one of the target object, and the rest of these objects are the copy of the real target object. This overall hardware system will send the data to PC via camera cable, this is the cable, and the Arduino cable, 6 and 7, these two, will send the data to 8. 8 is the PC. For the more detailed view of the sensing system, the picture at the left is the side view of the sensing system, and the picture at the right is the top view of the sensing system. In this case, the sensing system uses the base servo MG996R, and it's supported by the unused PCB board. Number 2 is the camera, number 3 is the ultrasonic sensor. Next is the object's color detection and tracking. So first, for the object's color detection, both pictures show that the blue target object is detected. The object's color detection algorithm is composed of several steps. The first step is to find each red, green, and blue pixels in the picture. Each of the pixel then is converted to a binary image, where the target color pixels will become the foreground, like in here. In this case, all the white pixels are blue colors, and the other color pixels will become the background. And from this picture, it is bounded by the blue box because this is the largest area. So the foreground with the largest area will be chosen. Then, the largest area from each RG and B colors are compared. The largest one will decide the color of the target object, while the picture at the right shows that the blue object is detected, as we can see in here. Next, for the object centroid tracking. So after the target object is detected, the object centroid need to be tracked. In this case, the camera width is 1280 pixels, so the middle frame width should be at 640 pixels. In this case, the target object centroid is 844 pixels. The solution is obtained by calculating the difference between this value with this 640 pixel value. And it will be fed back to the algorithm until the difference or the error is 0. In this case, the tolerances are given since the servo small step is about 1.8 degree. Therefore, the iteration of the system to achieve 640 pixels will take more time. To take less time for the iteration, tolerances are given. So in this case, tolerance of 1 pixel are given. So basically, the whole process will stop to track until the centroid object will achieve 640 or 639 or 641 pixels. After the object is detected and tracked, the target object coordinates can be calculated. From this picture, this is the sensing system from the top view. The target object is assumed at the specific position, and the sensing system is already aligned with the target object centroid, so it is assumed already aligned. In this case, sine rule can be used to calculate the target object x and y coordinate. For the z coordinate, it's always constant since the target objects have same height, so these x, y, z coordinates are sent to the PC for the robotic arm simulation. Next, I'll talk about the pick-and-place robotic arm simulation. This picture is the robotic arm model in Simulink software. This model is imported from the Solidworks software to the Simulink by using the Simscape multibody add-in. This is the Simulink blocks that are used to run the robotic arm pick and place simulation. So for the robotic arm trajectory, basically it will start from the home configuration. As we can see here, it facing like this. This is the home configuration. Then it will go to the target configuration to pick up the object. After that, it will go to the place configuration, which I assign in here, to release the object. Then after it releases the object, it will go back to the current target configuration. For more detail on robotic arm trajectory, the first step is that the base rotates to the target object configuration. The next one is the upper arm and forearm move closer to the ground, so the gripper will close. And after it picks the object, it will go to the next step, which is the upper arm and forearm will move away from the ground. Then the base rotates to place configuration for this step. And the next one, both upper arm and forearm move closer to the ground again, and the gripper will open. In this case, it releases the object. And after that, both upper arm and forearm move away from the ground. Finally, the base rotates back to the current target object configuration. So basically, it will replace the home configuration. So Q01, Q02, Q03 are the joint angle values for the home configuration, and Q1, Q2, Q3 are the joint angle values for the target object configuration. Q1P, Q2P, Q3P are the joint angle values for the place configuration. So these are the trajectory blocks that control joint 1. In here, the switch block, as we can see in here, 1, 2, 3, 4, will be used to control the flow for each trajectory step. So first, the trajectory planning will occur from Q01 to Q1, and after 10 seconds, it will retain the Q1 value, and after 30 seconds, trajectory planning Q1 to Q1P will occur. Then after 40 seconds, it will retain Q1P value, and after 60 seconds, trajectory planning Q1P to Q1 will occur, and at time equal to 70 seconds, the whole process will stop. As we can see in here, the overall one. And next, these are the angle, velocity, and acceleration result of joint 1 trajectory. So the yellow one, the angle trajectory, the green one is the velocity, the red one is the acceleration. In this case, the trajectory planning used the cubic polynomial function. It can be seen from the angle scope. It occurs at time 0 to 10 seconds, in here Q01 to Q1, and then it will remain constant for Q1, so from 10 to 30 seconds, and from 30 to 40 seconds, trajectory planning Q1 to Q1P. Then from 40 to 60 seconds, it will remain constant for Q1P value. Then it will do the trajectory planning Q1P to Q1 for the last 10 seconds. And this slide shows the trajectory blocks in Simulink for other joints. So this is the trajectory for joint 2, this is for the joint 3, this is for the left gripper arm, and this is for the right gripper arm. And this is the snapshot of the simulation process during picking the target object. The top left is the camera view while tracking the target object. The middle one is the robotic arm configuration when picking the object. The target object is one with the blue circle. The right one is the real-time sensing system from top view. It can be seen that the robotic arm end-effector has the same coordinate with the real target object in the sensing system. Next, I will go for the overall system flow. I'll explain a little bit and I will show the simulation demo. So first, the sensing system needs to be connected with the simulation software. Next, the servo will be set to increment for 27 degrees to scan the desired target object. In this case, it first scans for blue objects, red objects, and green objects respectively. During the scanning, the blue object is detected by the sensing system, then the object-centroid tracking is performed. After the sensing system is aligned with the target object centroid, the target object Cartesian coordinate is calculated. This coordinate will be used by inverse kinematic to obtain each of the joint angle. Then the trajectory planning between each configuration for each joint is set up. These parameters later will be sent to Simulink from MATLAB software to do the pick and place simulation, so it will open and simulate in Simulink. like this one, like I mentioned this in the previous slides. After the simulation finishes, the servo will rotate again with 27 degrees of increment and starts to do the process again. And once it reaches a 162-degree position, it will start to scan the red object, and the servo will decrement for 27 degrees until it achieves the home position. After that, it starts to scan the green objects, and the servo will increment for 27 degrees until it achieves 162-degree position again. Now this is the overall system flow. As we can see, the sensing system starts from the home position, then it starts to detect the blue object. Once it's successfully detected, it will do the object tracking for the blue object, as we can see in here, and it got 640 pixel value. Then it will immediately measure the distance between the sensing system and the target object by using the ultrasonic sensor. And then from here we can calculate the Cartesian coordinate, and the value will be sent to the Simulink. And in Simulink, the robotic arm will do the pick and place simulation, like in here. It starts from the home configuration, then it goes to the target object configuration. After it picked the object, it will go to the place configuration to release the object. Then it will go back again to the current target object configuration in here. So the next step, the sensing system will detect more blue objects. So this one is not blue and this one is blue. So it's successfully detected the second blue objects, and for now we are detecting the object center rate, and we got 639, and it immediately measured the distance between the sensing system and the blue object. Then the Cartesian coordinate will be calculated and sent to the simulation software. So as we can see in here, it goes from the home configuration in here, then to the target object configuration in here. It is picking up the object, and then it will move the object to the place configuration in here. Then it will go back again to the current target object configuration. And it will start to detect more blue objects. Once it reaches 162 degree, there's no blue object, so it will start to move in the opposite direction and start to detect red object. In this case, it's successfully detected. So we got 640 pixels of the centroid, and we are measuring the distance. It's around 5.8 centimeter, this distance. And then we calculate the Cartesian coordinate of the target object and send the data to Simulink for the simulation. So it will pick, it will go up, and then it will move to the place configuration. So it's gonna be the same process, and then it will detect more red objects, like this one. This one is not red, this one is red. It will detecting the centroid, then it will move, pick and place, and then place to the configuration. Then it's for the green objects. As we can see in here, the view for the robotic arm simulation is changed from top view to isometric view, so we can see more detail about the robotic arm simulation. So it's still detecting the object centroid. Since we want to have a very accurate data, so we limit to 639 or 640 or 641 pixel for the centroid value, and we got 641, and we measured the distance and then send the data back to the Simulink software. releases the object, then it will go back to the current target object configuration and will redo the process again. So you can see the sensing system is still detecting for the green objects. So this is the green one. So finally object is detected and it detects the object centroid of the green object, and it's at the center already, and the distance is 8 centimeter. Then it will rotate to this point. As we can see, it has similar coordinate between these and these one. Then it will place the target object in the place configuration. And finish. So all the 6 objects with different RGB colors are successfully determined. So the Cartesian coordinates for each of the objects is successfully determined by the robotic arm, and the robotic arm able to pick and place, do the pick and place simulation. Next, for the future improvement, implementation in real hardware compared to in simulation, and put more advanced object detection algorithms such as a neural network that can detect more complex object shape and colors, and use 6 degree of freedom robotic arm instead of 3 degree of freedom, since with 6 DOF we can control the end effector orientation. Thank you.